Okay, good. Sorry. Go ahead.
The title of our project is Improved Heart Rate Monitoring Through IR Plethysmography. I'm Lindsay Sanford, this is Rebekkah Merrill, and this is Divina. The purpose of our project was to create a better, cheaper, and simpler heart rate monitor, and we decided to use a plethysmograph. And what it does is measure changes in blood volume using a photoelectric sensor and a light source. This is a picture of a plethysmograph, and basically our aim was to create a heart rate monitor without the need for wet electrodes that you use on a regular EKG.
So basically what we did was we used actually an Ad Instruments model, MLT 1020 EC, basically IR plethysmograph, and what it is, actually the one we use is actually the ear component, but we actually tested on the finger to get better data. And typically when you have one of these, our sensors kind of look like this, where you actually have a part that connects into your PowerLab 26T. Because it actually uses data on the computer and like chart view or lab view to be able to detect data. We actually ran initial testing using the current IR plethysmograph with the PowerLab 26T, and we actually got this as our results. And this data is jumbled. You can barely detect anything. Obviously, it looks nothing like a heart rate signal, and these are due to noise artifacts. Typically, the PowerLab 26T contains like an internal filter to where you basically don't usually get as much noise. It's supposed to filter out that noise, but it wasn't in this case. So what you should get when you really measure using IR plethysmograph is this kind of data. But instead, we decided to tear apart basically the 80 instruments plethysmograph, and we actually stripped it apart, resoldered all the wires, connected it to an amplifier, industrial amplifier, an 8620 industrial amplifier, and we added a 510 resistor to it to get 100 gain. Then we connected that to a high bandpass filter, and this is our circuit diagram of what it would look like, a schematic representation. And basically what that did was it allowed to get rid of noise artifacts that were related to instrumentation issues or some of the motion artifacts, and it only transmitted the signals associated with blood volume change in the finger. And so when we did this, we actually got data that actually looked more like an EKG signal, because you have like a small P wave, what looks like a QRS complex, and a T wave by doing this. We actually have a video of what my heart rate looked like originally, and so you can actually watch my heart rate across the monitor. And then, like, basically you can actually turn on our oscilloscope in our device, and you can connect it to your finger. And if you put your arms down by your side, it actually, oh, let's see if I can.
Yeah, I can't quite see it on the video camera.
Yeah. If you put your arms down by your side, it's supposed to clean up the filter. There it goes. Oh, pause. There it is. Well, there it goes. And you actually get your heart rate, or what it looks like in the changes in blood volume if you remain still. And you can run stop your data. I want to run stop. And you can calculate your heart rate by this, and Lindsay's going to tell you how we actually determined your heart rate.
So first, to get the heart rate, we had to determine how many squares on the screen of the oscilloscope represented 1 minute, and we decided, or we calculated that it was 240 squares, because each little square is 250 milliseconds. And we can use this formula, find the number of squares between the peaks, and do 240 divided by that number, and that gives you your heart rate. And based on this data, we averaged the heart rate for each of these peaks, and we got 95.7 beats per minute.
So basically, I just need to exercise more to get a lower resting heart rate.
We had a lot of issues with this device at first because one of the wires were frayed, and we had